Okay, welcome to our systems engineering course, and today we're going to cover chapter 2. It's called Bringing Systems into Being, and in here we're going to take a longitudinal view at the systems engineering process in the context of product and project development. And one key concept that we're going to discuss is the concept of the life cycle. And after you go through this, it basically, you realize that it's common sense, and it almost seems trivial, but you'd be surprised that most people involved with product development don't think about it, okay? And in a nutshell, what it means is that products have a life cycle. It's not just to get a prototype or a few prototypes. They are going to do something later on for the benefit both of society and financial benefit of whoever is investing in this development. So, but everything that happens after that product is released and you have the prototype and you feel so good that it's working has an impact, a retroactive impact in what you do in that first phase of design. So what that means is that you have to look forward to make sure that you do the right things earlier. So that's the nutshell of the chapter. So we're going to see what that entails in terms of the discipline and the tools, the conceptual tools that we're going to be sharing with you. So to do that, we're going to start by defining the type of systems that we said that we are discussing in this course. So we are discussing synthetic engineer systems. So more specifically, what that means to us is that we are going to be discussing technical systems. Now we'll see later that there is a part on the enterprise of bringing systems into being that there is a business aspect to it as well. There is a schedule, there is a budget, there are resources. So that falls more on what we would call program management. So we're not going to dwell on that. We do have a course on that if you are interested. And so we want to basically not or overlap as little as possible with that body of knowledge. We want to focus more on the technical aspects, but we'll see that we really cannot completely decouple from the business implications of what it means to bring a product into being. So to go forward, we have to define this engineer system, and some of this we treated in our formal definition of systems. And we have to remind you, or we want to remind you, that these systems have a functional purpose and is in response to an identified need. They also have the ability to achieve some stated operational objective. They're also brought into being and operate over a life cycle, beginning with the need and ending with phase out and disposal. They are composed of a combination of resources. They are composed of subsystems and related components that interact with each other to produce the system response or behavior. They are part of a hierarchy and are influenced from external factors, from larger systems of which they are part, and they are embedded into the natural world and interact with it in desirable as well as undesirable ways. So I just read that, and I'm not a fan of reading stuff to you, but I did that so I can go back now and elaborate by means of the terminology that is in italics, and that is part of the terminology of systems engineering. So systems have a functional purpose in response to a need. The word need is important. We design products and systems in response to a need. There has to be a need, and normally the catalyst for a need is a market-driven need that someone has identified, that someone sees a business opportunity tied to that need. When you respond to a need, when you solve someone's problem, they're usually willing to pay you money for it because they have a need. You're going to satisfy that need. There is a demand, so you're going to respond to it. So you have to start there, understanding, and also understanding that not all the understanding of stakeholders that start with or bring to you this need are really needs. Some are wishes, some are nice to haves. So part of the system engineering process is actually to distill real needs about what the concept is. And we're going to see that both qualitatively and quantitatively. So from that, you can then come up with a functional purpose. And it needs to be very well stated because everything is going to come from there. That's the genesis of the product. And from that, you can get, if you have a functional purpose and it's clearly articulated, then you can get very clear operational objectives for the product. Then we're saying that they are brought into being and operate. They operate. This is not good enough to have a prototype. They need to operate over a life cycle. How long is that life cycle? What is the environment over the life cycle? Does it change? What are the requirements? What needs to happen over the life cycle and the characteristics of that product over the life cycle that is going to influence what you do at the very beginning of the design conceptualization. So that we're going to see how we do that. So they're also composed of a combination of resources. We said that, and this is broader than just components because we have the next bullet talks about subsystems and components that interact with each other. So that really tightly coupled with the definition of systems and the hierarchies of systems, both logical, functional, and physical. But a combination of resources is broader. So we're talking about the resources that need to come together to make this system realizable. And part of systems engineering is figuring out what are, for example, these different engineering disciplines that you need to develop a product. Because if you understand well the product up front, then you have a good view of what you need from an intellectual perspective, from a technical perspective. What are the disciplines that you need? What is the expertise that you need? So that's what we're talking about with the combination of resources. So it's a superset of not just what the system entails, but peripherally, what is the collateral? We call it collateral resources. It could be documentation. It could be repair and maintenance concepts and facilities. We're going to look into all that. So the next to last one is also closely tied to the definition of system. We know that we're going to have some hierarchies, again, that are functional, logical, and physical. When I say physical, I also mean they're geographical. It could be that the geography is taken into account. If you're talking about, for example, a supply chain system. And then the last one talks about that these systems are embedded. They live and operate in the natural world because at the end of the day, we are in a natural world. So everything that exists in this natural world is interacting with it to some extent. And we have to be mindful that those interactions can be undesirable as well as desirable. So maybe that is a cat about. You have to think about that. So all these issues may seem, after you think about it, may seem, of course, it's so clear, but you'd be surprised that they are not front and center as part of the methodology of design. So it is not in our nature because they are not in the critical path necessarily. So you can get prototypes by ignoring a lot of this. You're still going to get a prototype, but the problem is going to come later. The problem is going to come later. So how do we counter our human nature of taking the path of least resistance, right? So we accept that. How do we counter that? Well, we counter that with tools and methodologies and systems, putting those in place. And that's what we're going to be talking about those throughout this course. And I remind you that, remember that this is we're not even being discipline specific to electrical or computer, is broad and is general, because we want to offer something that you can use for almost any type of project. And again, the key is for you, if you're doing a specific project, to identify what is applicable. And to get that, and the tools that we are presenting here, and adapt them for the benefit of your specific endeavor. So this is a follow-up to a lot of what I've said, and we want to expand on why is it that taking into account these methodologies enhances product competitiveness. So for one, if you have a rigorous way of identifying customer needs and distilling system requirements from that, you have a way of truly answering and meeting those needs. So, and that is one of the best things that you can do in a product, is to actually meet the needs in a very specific way without over-designing, because you can always over-design and you have a larger chance of meeting the needs, but you also may be putting things there that are not necessary. So that it increases the cost. It reduces your competitiveness. So that's one part of it. The other one has to do with you'll be able to address not just these needs at certain points in time, but throughout the life cycle of the product. So there are no any issues later on. By understanding all the system requirements and applying the system engineering techniques, you're going to be, because part of it is developing these hierarchies, you'll be able to consider all part of the systems in a holistic way. So you'll be able to break down the system into subsystems all the way to components, consider all the different parts in a very systematic way, inputs, outputs, processes, and what are the interoperability requirements at the interfaces. You'll be able to recognize what are the engineering disciplines that you need. I talked about that. How does the team need to look without having resources that are superfluous in the context of the development? And also, we'll see that we'll have a disciplined approach to reviewing designs evaluating designs, and also building feedback into the process of developing products so that you have the largest likelihood of success. No system is 100%. There are no 100% guarantees, but, and this is also from my experience of many, many years, this gives you the best chance for success. There are a lot of projects that don't see the light of day. There are a lot of failed projects. You just don't hear about it. You hear about the ones that are successful, but there is a large percentage. The ones that you hear about, successful ones, are a very small minority, actually. So there is a lot of room for improvement, and that's a good thing, because I would say there is almost no way to go but up if you follow these techniques. So let's take a first and very simplified view at this life cycle. And we're going to start by breaking it into two parts. First is what we're going to call the acquisition phase. And that's where you have your system to a point that is ready to be deployed. And when it's deployed or put into operation, we call that the utilization phase. The first one we call acquisition because maybe part of your development, after you go to the process, the best way of developing the system is to acquire it. Maybe you don't develop it. And we'll talk about the trade-off in later chapters. How do you look at trade-offs between what is called the make versus buy decisions, and how you look at that. So in the acquisition phase, as we mentioned, you start with a need. You're going to go through these three big steps: conceptual and preliminary design. Those are going to be, for us, chapters 3 and 4, as we cover them later. Because remember, we're focusing on the beginning of the process, putting all the disciplines in place, but with a view throughout the life cycle, okay? A holistic view ahead. Then we have the detailed design and development. This is actually when the actual design happens. Then we have production or construction. It could be just a massive construction project. That's also a complex system. And then again, when you put it in the utilization phase, that's when the product gets used. You need to worry about support and phase out, and in some cases, disposal. So that's the first view of the life cycle. Simple. So now we want to layer down some more detail and look at how the system engineering approach that we have been talking about allows you to start looking ahead. So for example, for production operations, which is that third big step, during conceptual and preliminary design and being executed during the detailed design, we are going to be looking at aspects of manufacturability so we can start designing the manufacturing configuration so that the design not only works, but also can be manufacturable. So at that point, if we look at manufacturability at the beginning and start looking at what are the requirements and asking the right questions about, is this design going to be manufactured a certain quantity effectively? And that may mean when you choose a part, maybe it's not enough just to choose a part that does the job, but to look at the supplier. Look at the supply chain. Is it going to be there, not just now when I did the part for the prototypes, but is it going to be there a year from now when this thing is ramping to full manufacturing? That's important, because if you have this prototype, but then later when you're going to start ramping to production, the part is not available, that is very disruptive. Now you have to go back and redesigning a substitute or a replacement. And whatever qualification methodologies you did, you have to repeat that now because you changed a variable. So looking at things like that. On the utilization phase, for example, for the support and maintenance, if you start worrying about during the conceptual phase, what are the things that need to be in the design to make it supportable and that it can be maintained easily, this is very important, because you may have something that works, but then it cannot be supported or maintained. You can do things at the design level to make sure that this product is effectively maintained. So that, again, is looking ahead. And even things like retirement, phase out, and disposal, which could be part of the natural life cycle of the product, or it could be an intentional phase out. And that may have implications on your design choices at the beginning. So phasing out and obsoleting products is actually an effective business technique. So we all know how effectively Apple has used that technique to basically obsolete their own products and cause new revenue streams through different waves of iPhone releases. That has been very effective. And they know that if they don't do that, then Samsung is going to do it for them. That's not cool for Apple. So that's a little bit of business implication also in the system engineering approach that we take at the beginning. So this is kind of just a little bit more of detail, but in reality, the life cycle is much more complex than this. There are a lot of details, and now is when it really gets interesting. So this is an eye chart that I won't be reading to you word by word, but I will be highlighting certain things. This diagram is in your book, so important for you to, after this lecture, you can go back to the video, you can pause the video and read it from the screen. But what I would do is basically find this in the book and spend some time reading and thinking about this, trying to project myself into a real product development situation and how does this would apply to what I'm doing. Because you have to exercise your mind and get used to thinking this way. So let me highlight some things, and this is only view one. I'll show you another view. I like this one a lot, but essentially we start with that definition of a need over here and the exercise of conceptual design. Now this diagram recognizes that new concepts for products rely on existing either research, which you have to do and mature to get you to an existing technology, or you have to understand and be very aware of existing technologies, and that's why it's so important to know what's available and keep current with technology, and that's part of that lifelong learning, because it's very important to know what's available so you know what you can do. So that is an input into this process. And the elements of this conceptual design process is that we're going to look at the feasibility, how we identify the need, how we plan the system, the functionality, distilling the system operational requirements, maintenance and support concept, and performance measures. So key here is system operational requirements. What is it that the system needs to do? And performance measures is how well does it need to do it. And at this point, we have a lot of information. We have done a lot of forethought about what the system is going to look like. This is this process we're going to cover in detail in chapter 3. Then we go into this preliminary design, which is also called advanced development. And we start looking at the functional analysis. Now that we have the functional, the system operational requirements, we start looking at the system functional analysis. And if we understand what the system needs to do, we start diving deeper into what is the functionality required for maintenance, because we already have a maintenance concept. And if we understand well what the system needs to do from a functional perspective, we can look at trade-offs of how to achieve that functionality. Notice that everything that we did over here in the conceptual design has nothing to do with how we're going to design this system. It's all about articulating well what the system needs to do, because if you do that, then you have a very clear roadmap to address how. You cannot have good hows without understanding the what's well. That's a key thing to understand. So once you have a good view of the functionality of this system, you can start synthesis, which is developing the hows, an allocation of those design criteria, and you can start allocating performance factors and effectiveness requirements, and allocating the support requirements, and analyzing that what you have thus far. So now you're starting to, at a system level, synthesize something and developing the hows of the system. Then you do system and subsystem analysis, which is basically repeating the same methodology at a subsystem level. And once you have that, you can start doing some modeling, physical prototypes, mock-ups. We'll discuss that. So this here is going to be our chapters 4 and 5. Okay? And so essentially chapter 4 and sum of 5 is going to be here as well, the detailed design and development, where you actually finish your design. But first you have to do detailed design at the system level as well, and have reviews and do some more modeling. But at the end of that detailed design part, you have actual prototypes that you, part of modeling and simulation is to test your concepts at that level. But when you do have something, you have to have the different types of evaluations as well. And this box is specific here is chapter 6, and we're going to talk about those processes. And then your system goes into production. It goes into production, it goes into utilization and phase out. So this is the view, very detailed view of processes that take place during the life cycle, noting that through this process there is a mechanism of feedback. So you can always go back to a previous step given the information that you find in a step that you are in. So again, there is a lot here, and I mentioned the main things about it, but this is something to be read slowly and internalized and studied. So you need to do that. So I'm going to show you then a different view of the life cycle. So again, it starts with the need, ends with retirement. And it has here, in even smaller letters, these are pretty much a lot of the same processes that we discussed. But here you have those big steps: conceptual, preliminary, detailed design and development, production, construction, operation, and subsystem and system support. Through that, I'm going to drop here, and each of these processes sequence has been depicted as a waterfall model, which you may be familiar from ENG 142. I was involved in that, and at some point we put something about the waterfall design cycle in there. So again, the waterfall is sequential with some overlap, and then there is a feedback mechanism. That's the main thing there. So each of these big steps are here depicted through their processes through waterfall models. And then in the middle here, we have something that the other view doesn't have, which is the ties into program management through milestones. So these are important milestones that you can actually make part. So you can start seeing now that when you go into your senior project, one of the first things that Dr. Katz is going to tell you is you have to have a schedule. And well, here's basically a skeleton of a schedule with milestones that you can adapt to your own project. So functional baseline, that is at the end of the conceptual design, and the outcome of that process, of that conceptual design, is a specification. It's a system specification of what we call type A. And this has been vetted and developed by a lot of smart people with a lot of experience through INCOSE, which is the equivalent for systems engineering of IEEE for electrical and computer engineering. And they have an outline, and you'll find this outline in the book, and you will have to write that as part of your project. You're going to have to do an outline. So this system specification type A is essentially a questionnaire that guides you through a sequence of questions, and if you answer these questions about the system that you're considering as part of the processes of conceptual design, you have no choice but to have a good understanding of your system. So we are giving you that as a tool, the outline of a type A specifications. Then after preliminary design, there is a milestone, which we call allocated baseline, that has other type of specifications and development specification, process. You may need to specify a process. For example, the process of manufacturing is specified through a type C specification. So you may have to specify other products, material. All these types of specifications are outlined for you as questionnaires that you can basically adapt to your own case. We call those types B to E specifications. And then after detailed design and development, we have what is called the product baseline, which we can have add to the previous specifications or we can do the same specifications at the subsystem. At that point, we have that. So we can design everything and go into production. So you can see the other baselines there. And also towards the second or the bottom of that second part, there are reviews also as part of this baseline. So we have conceptual design review or system requirements review. We're going to talk about that in detail. System design review and equipment, software design reviews, and critical design review before we go into production. The elements of what needs to be discussed and touched upon in these reviews are also given to you as or we're going to be discussing them, tools that you can use. Okay? So this is another view. Again, this is another one to spend some time with, read, study. So these two, because they're busy. They're busy, so anything busy like this is just for me to bring it to your attention, but the best way is not for me to read them to you or talk about it, because it'll take me a lot more time than we have. You do have to spend some time with it. But I'm giving you the gist of these diagrams. So since we talked about the waterfall model, I wanted to, at this point, introduce three very popular system process models. There are many others, but three of them, and you may be familiar with the waterfall, but there are others, and I wanted to go through those. Of course, you know, everything that I say is in the book, but let me go to the first one and reacquaint you with the waterfall model, which basically have the big steps of product development as a waterfall of sequential but overlapping major processes with feedback mechanisms between the different processes. And those major processes are requirement analysis. There's a lot there, but not only because if you're going to do requirement analysis, you have to get the requirements before you analyze them. And once those requirements have been analyzed, and the outcome of good requirement analysis is that you know whether you have good requirements or you keep at it through all these smaller processes in the conceptual system design phase until you have good requirements. And then you can translate that into specifications. So requirement analysis and requirements definition is to come up with good whats. Specifications is to come up with the hows to address the whats. Then design. Design is to implement the hows. And you have, from a design perspective, but you are implementing the hows. The implementation here is the actual building of that design, coming up with, let's say, a physical implementation, a prototype at that point, or pilots, or whatever it is that the project requires. Then you have to test. And also that implementation, I want to go back because this is very broad. That implementation may also be the actual construction and production and manufacturing of this. And when we say test here, broadly and loosely, we're maybe talking about not only the test of the prototypes, but also the test for manufacturing. We're going to see that one thing is to test for, was it designed correctly? And another one is to test for, was it manufactured correctly? Those are two different types of tests. And it may require that you do things in the design to allow for either or both of those. You may have a design that is perfect, but that doesn't mean that it was manufactured correctly, because no manufacturing process is perfect. How do you make it easier to catch those issues? Because as far as the end customer is concerned, she doesn't care whether the problem is because it wasn't designed correctly or it wasn't manufactured correctly. The end result from the customer perspective is the same, and that's what you want to avoid. You want to ensure customer satisfaction. And then, of course, after you test, then there is a maintenance. So this is the most simplistic depiction of the system engineering process throughout the life cycle, which is the central theme of this chapter. And then there is the spiral process model. This process or this model is interesting because it groups activities from a functional perspective. And what I mean by that is that the timeline, starting with a need, the timeline starts at the center and goes along the spiral. And then along that timeline, we have different activities. You can see here. And then you can see that the activities have been grouped radially going out. And of course, since the timeline is on the spiral, as you go out radially, that means that time also is going out, or is the further you are from the center of the spiral, that means that's later in time. But the fact that these activities have been grouped radially in this radial columns here, this model claims that these activities are functionally similar in nature. And that's helpful if you're trying to allocate these activities to different set of people with a specific or specific resources, with a specific knowledge, expertise, and so on. So for example, if you may have someone that is doing or championing, because all this is always a team effort, someone that is championing the requirements. So these are here: system required determination, function definition, detailed requirements. So that is a similar in nature type of activity. So you could assign that to a specific team, a specific person, and maybe someone else is doing the system analysis, the trade-off studies, and the evaluation and optimization. That could be grouped together from a functional perspective. So this is something to keep in mind for that purpose. So again, there is a lot more detail here. This is a good candidate for you to spend some time with. Like I said, I could read all this to you, but they are there. Again, you can watch the video, stop it, think about it, or it's also in your book. Then the third model that we want to cover is what is called the V process model. This actually works well with products that have electronic content in them, because it takes into account very effectively the hierarchy. And in products that are dominated by electronic content are hierarchical in nature. You have chips, you put on a board, the board you put in some box, the box you put on a rack, and so on. So you can easily see that hierarchy. And even though we have been talking about physical as well as functional and logical hierarchy, a lot of the time in reality these hierarchies coincide. But I don't want you to make that assumption. That you need to come to that conclusion from a rigorous system analysis. But the end result is, as you may expect, is that it makes sense that these hierarchies coincide. Okay? So this model takes that into consideration in the sense that you do what is called system decomposition and definition. You do that tops down. And you have experience and you have taken courses where I have talked to you about the importance of understanding top-down versus bottom-up design and implementation. So the definition, the conceptualization and on the design part is tops down. That's the best way because you start at the system level defining what subsystems you need and eventually, let's say, defining what components the subsystems require. So that is depicted on this left-hand side of the V, defining system requirements, allocate system functions to subsystems, detailed design of components. So you have all your design done and specified and executed. Then the right side of the V is a bottoms-up, what is called integration and test. So you have had courses where I have told you start testing something small and make sure that you then deem that a known good entity before you use it on something larger, because if you just put everything together and test at the top, then it's very hard to diagnose issues and debug. That comes from really understanding this B process model paradigm. So once you have these components designed, you verify the component, you put the components on the subsystems, you verify the subsystems, you put the subsystems into the system, and you verify the system. That part is called integration and test. Throughout this, you are always testing at some level, whether at the component, subsystem, or system, but you're testing to the requirements that you previously defined at that level. And the reason it works is because if you did verification bottoms up through the hierarchy, you don't need at this level, at the system level, you don't need to worry about the component anymore, because if you did a good job verifying the component here according to a good component design specification that you created, then the component is good. You cannot worry about everything because systems are very complex. So what you are worrying here is your subsystem level interfaces and functionality at the system level. So this has a lot of, this resonates and fits well with electronic type product development, because as you can see, even this this here that we have, so we have here this equipment here for our media, and we can see that there are boxes on the rack, that's the system, but there are boxes there, those are subsystems from the perspective of that system, and inside those boxes there are boards. You can say those are the components. But you can even say the board is a system and then the components are, let's say, the chips. So you can keep, but for the purposes of matching our media center here to this, I would say the components are the boards, the boxes are the subsystems, the rack, the complete rack is the system. So you can see that. Okay? So, changing gears a little bit, I want to talk about all these design considerations, and the key here is design, you're going to have a methodology for considering all these things, all these aspects at the design level that influence the success of the product throughout the life cycle. Again, there is a handful of them there, but I'll talk to some of them more than others, but let's just say and start with the technological feasibility. So we talked about that. That's something that needs to be considered. You may have to worry about social and political feasibility. Just because something is feasible technically doesn't mean that it is feasible from a social or political perspective. That may be a care about. You may have to consider that because these are things that go into society. So it may be that you need to worry about environmental sustainability of your product, and just the sustainability of the system itself. I mentioned supply chain and things like that. How you design the system, you may have to do things at the design level to ensure that your system is flexible and expandable, because you may want to expand the system. Maybe you cannot have all the functionality to meet certain market window, but you don't want to have to redo the whole thing. So you put hooks into the design to be able to very efficiently expand it. I also talked about the being able to support and service the system. Compatibility, very important. What are the interfaces? What does it have to interoperate with? What standards do we need to use? So these are all considerations that affect your design. That is not just does it work, and even does it work well. The affordability and profitability, that's central to any real system. If we're doing something, you're getting paid for it, somebody's investing that funding so they can get something out of it. So there is a business aspect to it. So performance and functionality, of all these boxes, what I've been saying is that people normally just care about this, and actually not even about both of them. Maybe people tend to focus just on the functionality. But how many other things are there to make a product successful? Can be manufactured? What type of quality level and robustness do we need? I can tell you that it's very easy to get one of something to work. To get thousands and millions of them to work reliably, that's a whole different story. But unless you can do that, you won't be making any money, and whoever funded you to do this product development enterprise is not going to be happy. So quality, which means how robust and how well and functional the system is at time zero after manufacturing, and then also reliability, which is for how long does the system maintain the quality level, and also how well can you maintain it. And again, you may have to worry about how recyclable the product is and the disposability of it. And ultimately, if you are interacting with humans as part of the mission and operational requirements of the system, what are the human factors and safety? All these are considerations of design, and we don't think about it unless we have some type of methodology. It is not natural for us to be remembering all this, just because it's a lot of it. So these are the tools that allow us to do this effectively, systems engineering. Now let's take a look at the decomposition of system design requirements, which we're going to start doing here. And this is basically the next, most of it is in the next chapter in a lot of detail. But it's so important to repeat so hopefully by now you are convinced that it's important to define the need and to separate the need from nice to haves and you know what we wish to have, to really articulate needs. We're going to have a tool for that. So we can get good requirements. And here's some of the processes we discussed: the feasibility analysis, getting the operational requirements and articulating those. Maintenance and support concept, we're going to go exactly through what that means and through examples. And then define the technical performance measures, which is, again, how well the system performs its mission. Then we're going to start doing the design evaluation and identify what is called design-dependent parameters. Those come from both the operational requirements and the measures of effectiveness, or the technical performance measures. We can start analyzing trade-off studies, and we can start then synthesizing, basically coming up with the hows, because at this point we have good whats. We can also do that at the subsystem level, because at this point we have identified what our subsystem is going to be, and these hierarchies start emerging. In subsequent chapters, we're going to look at methodologies to decompose and come up with the hierarchies of a system. And I do want to remind you that through all these processes, we have feedback mechanisms through reviews, which we're going to be talking about as well. Now, one thing to understand is that not everything is equally important. So to say that all of this is important, yes, that's one thing, and that is true. But I do have to add that not everything is equally important, and you cannot worry about everything at the same time. For example, we have here, we're showing you tiers. We're showing you tiers of design considerations. And a longer and even more expensive list than the previous diagram that I showed. And they are tiered. What it means is that the higher the tier here, the more important these considerations are. And you have to make sure that you have a good handle on the higher tier considerations before you really address the lower tier ones. They are all important, but there is a prioritization of importance. Here, we also show two legs of considerations. The ones on the left are those that are more on the program management, resource scheduling type of side. So we are not really going to dwell on those. But the ones on the right, the technical factors, those are very important from a system engineering and technical and engineering perspective. So we really want to understand those. So the first order consideration, at least from the perspective of this diagram, is system effectiveness, which in a nutshell is the system performing its mission and its functional requirements effectively. Now, also, considerations are a lower tier support, from a bottom-up perspective, this bigger and more important considerations at the higher tiers. So you can see in the second order considerations things like performance, availability, operational availability, which is, things go down because they require maintenance or because they break. So you may have a requirement that the system needs to be available certain percent of the time. Calculating from that number, how do you take into account reliability matrix is outside the scope of the course, because the course is designed to be qualitative in nature. But I can tell you that there are, for different types of systems and different materials and things of that nature, there is a well-defined body of knowledge to quantify reliability metrics. So there are people that are reliability engineers, which that's what they do. So you can see here the second order considerations, things as dependability, producibility or manufacturability, interoperability, support, sustainability, and disposability. So these ones are kind of like what we talked about. Then we have third order considerations, and this is just a guideline. It may be that for your project, something that shows up here as a third order consideration, maybe for you it needs to be like right at the top. What we are showing is the methodology of you sitting down and listing considerations for your product that are applicable, and we are trying to make you sensitive to the process of prioritizing them, because not everything can be equally important. So if you're working on a wearable, maybe size and weight is at the top, because that's the nature of the product, and that may be, and you got that by getting a good articulation of what the need is. So this is just an example. So you can see others there. And again, I'm sure that, this is a busy diagram as well. So anything that is busy like this, I do want you to go back and review and study. But the main idea here is that you have to identify your considerations and basically group them in tiers so you have a good view of the importance. Then you can make decisions. You cannot make decisions if you don't understand the different levels of importance of the considerations of your design. And that goes directly to the trade-off analysis that is part of the process. So as we wrap up the chapter, just a few more things. Through all these processes, the main thing here is that we are going to be doing evaluation of something, synthesizing, that broadly means creating something or grouping or coming up with requirements or considerations. Something is going to, there is an output there. And then analyzing, which is testing those outcomes again against what you started with. In this case, maybe requirements, some type of requirements. Evaluating what you, now that you analyze it and say, yeah, this is good, you evaluate it further, and then you may be doing more synthesis. This is not an infinite loop. Eventually you do move on, but is the relationships between synthesis, analysis, and evaluation and how they feed each other, essentially. Then I also wanted to show you a morphology for product realization that takes into account a lot of what we have discussed so far. Is the almost like a flow diagram of the whole process through the life cycle from a system engineering perspective, and I want to highlight this up. On this side, you have the applied research or technologies, so that came up in our discussion. Feeding our development, which has a bottoms-up element to it and a top-down element to it. Now I'm going to jump to this side and say that here you have a customer that has needs, and those needs go into this needs definition, functional definitions and requirements, and those requirements go to the design team. The design team has a design, because part of knowing what your requirements are is that you know what your team needs to look like. So that team and the requirements go into this design synthesis function. Now here at the bottom is a system, subsystem, components, database of knowledge and things like that, which is tied to the bottom-up structure. And your design synthesis, after it happens, together with the knowledge that exists, gives you something that you can start doing first at the modeling level, some estimation and prediction, because remember that the design is, this is just at the very front end. At the conceptual level, the design is conceptual in nature. There's nothing physical in this diagram. So you can start doing modeling and then evaluating the design again against known data and coming up with actual information. So information is not the same as data, but you come up with information that can be used and judged against the original requirements to make decisions that benefit the customer. This flow is the essence of why this process is important. Because you end up with the customer making good decisions. At the end of the day, is the customer's project is their decision, but you as an engineer, as a professional, your job is to provide good information so that your customer can make the best decision possible. That has a huge ethical implication. But that's what we're supposed to do. Anyways, again, as we wrap up, just wanted to remind you that systems engineering, although it came from the aerospace industry, because of the complexity of all systems, has found applicability in all types of domains. Okay, so that's just, I think that's very clear at this point. And the last two slides have to do with, now that you understand all this and that we have talked about these specific activities of systems engineering from throughout the life cycle, I wanted to show you these curves that further go to motivate the usage of these types of techniques, and they justify even more. Why do you want to know as much as possible the system and influence the design as early as possible? Why do you want to do that? Well, because the further you go out in time, the ease of change of something drops quickly. So you want to change things over here when the ease of change is high, and ease is a proxy for cost. If you have your whole system design now, let's say go back to our media center here, it's designed, but you find that there is a problem because now you have to change a board. That's very disruptive because it may be that now the boxes don't work together and you have to go inside the box. So there is this rule of thumb that every time you go one level up in the hierarchy, the cost to change something is 10x. So if you are at the system level and you have that defined and you have to change something 3 levels down and you normalize that cost, that means the cost is going to be 1,000 the time if you have found it at the very beginning when you are really working at the level of the component without having it integrated. And you can only get that if you follow these methodologies. Also, of course, this curve here that says the commitment to technology and things like that, configuration, performance, cost, etc., is low at the beginning and then basically is very high. This curve is essentially just the inverse of the curve here of ease of change. So it's easy to change because you have not committed anything. So that should make sense. Then also, the more you defer without impacting your timeline, but the more that you defer by judicious and thoughtful system engineering discipline, the further you can push the inflection of the cost curve, you're making money, because if you delay expenses, that's like there is a time value of money associated with every type of cash outlay. So the more that you delay your expenses, that's economically that's good, as long as the overall timeline doesn't get affected. So we're talking about pushing the inflection of this curve out by spending more time here and then swiftly executing and spending later because you know exactly what you have to do. And the other curve shows that system-specific knowledge also ramps up in this fashion, which is your resources. These two curves are tied, that you can also defer your, what we mean here by system-specific knowledge is the specific knowledge for each specific domain, specific expertise, and so on. So you can defer all that if you really do a good systems engineering discipline approach. So, and if you do that, basically what this is saying is that at the beginning of a project, your system engineering need is highly influenced, is high, and the design is highly influenced by the system engineering approach. And then you can let the experts and specific disciplines take over as the system engineering role ramps down. So that's the relationship of the system engineering approach throughout the life cycle. So this is chapter 2, and I want to know if there are any questions that you want to bring up, or any slides that you want me to go back. Anybody? Yes.
The life cycles, like the process models, there was a feedback component to some of them. Does that mean that, like, should it be necessary, you could go back to a previous step through, like, the feedback loop? That's what the implication.
That's the implication, and not just to the one just before it. You can go to any other, and the mechanisms for that are the design reviews and things like configuration management, and we'll look at all those processes. So again, the question was about the feedback in the system engineering models, and yeah, the feedback mechanisms are there. We'll go through the specifics, and they are very important. Any other questions or comments? Yes.
Would like the upgrades of the system, like say you're gonna like upgrade the software or something like that, would that be under like the maintenance, like when you should like the aero guy?
Yes. For example, you're familiar with what is called over-the-air firmware updates. So your Android phone tells you, system upgrade, don't touch it, leave it there. Well, previous generations of phones didn't have that. We had flip phones, you don't remember, but there were no upgrades. You had to maybe connect it to a USB and to a computer that would send you something. There wasn't that ease of use, but somebody had to put possibly hardware, but certainly firmware to allow for that, and that needs to be part of the design requirements, and that could go. That can be said for any product. So it's part of the looking ahead at the maintainability, upgradability of the system. So we're talking about over-the-air firmware updates in this case. Yes. Any other questions or comments? All right, great. So this is the end of the chapter. Thank you very much.